And we are back with our exam 3 practice problem 1. So PK forces, resolve shear stresses. So I have the following ceramic material on the opposed stress state in MPa, isotropic linear elastic cubic ceramic material. So my Young's modulus is equal to 300 GPa. My nu is equal to 0.2. My shear modulus is going to be equal to Young's modulus over 2, 1 plus nu. So I could start basically including all of these values in my Mathematica notebook. So I could say that y is equal to 300 times 10 to the 9. My nu is equal to 0.2. My g is equal to y divided by 2 times 1 plus nu. And we've got those values there. We've also got that my sig, my stress state is 18, minus 16, 67, then minus 16, 17, 0, and then finally 67, 0, 0, and then times 10 to the 6. So that's my stress state there. And you can also see we have a deformation mechanism map. I also have a left screw with the tangent vector t is equal to minus 1, 0, 1. I also have, or I know that then my Berger's vector, if it's a left screw, it is going to be anti-parallel, so it is going to be 1, 0, minus 1. So there we go. And then I also know, well, actually my normal is going to be a little bit problematic because it's basically a PK force. But anyways, so we've got that. All right, so now let's see what the problem is actually asking us. So calculate the PK force on this dislocation. So my PK force, I know I could actually calculate the following. So the PK force is going to FPK of the stress, which is my sig, dot B, and then cross with T. So that will be my PK force. So there we go. So tangent vector, Berger's vector, we are good to go. Now, what is the resolved shear stress here? Well, resolved shear stress is a little bit tricky. Why? Because I need to find my alpha ij, my Schmidt resolution temperature, but if I do my definition cross T cross B, I get 0. Because there is no glide plane, we can't use that definition for the screw dislocation. So we unfortunately cannot figure out the resolved shear stress in this particular problem. So will the dislocation undergo dislocation glide or climb? How would you calculate the velocity of the dislocation motion? So again, for this problem, glide or climb, we can look at the component essentially that's going to be moving along the Berger's vector. So we have that, PK force here, so we could kind of see where there's going. If we have to calculate the velocity of the dislocation, we need to see, is our resolved shear stress tau, is it greater than our lattice resistance, or is our tau less than the lattice resistance, LR? If our tau is greater than lattice resistance, then the velocity of the dislocation will scale as our strain rate. If it is less, it is going to be thermally activated, so there's going to be some Arrhenius relationship, exponential minus an energy over kT all over temperature. And that will be essentially how our velocity scales essentially here. What size nucleations are created? So remember, we know that our critical shear stress is going to be equal to GB over 2 pi L. So with these values, you can go ahead and calculate that. I want to know another scenario where we have removed the applied stress and included an edge dislocation with a tangent vector 001 and Berger's vector. So here we go. So now I've got T2 is equal to tangent vector is 0, 0, 0, 1. Tangent vector 2, or Berger's vector 2 is equal to 0, minus 1, 0, minus 1, 0. What is the force that this dislocation exerts on the left screw? So I've got my tangent vector, I've got my Berger's vector. So this is for an edge dislocation. So I need to figure out and actually find, and actually I'm going to go ahead and cheat just a little bit. Here is my stress of my edge dislocation. Hopefully I have it somewhere else here. but I could just put it up. Yeah, we're gonna have to clear. Let's see if I have got it. I'm trying to look for, here we go. This is the edge stresses, and I could look at this value here to see what are the actual values there. But here's the function for, this is the stress tensor associated with an edge dislocation. So I can go ahead and find my FPK 2 of edge on screw is going to be equal to edge stress dot B, because again it's acting on that, and then I'm going to cross it with my T. And there will be your values. Excellent. Where will the vacancies and dislocations diffuse into for these two defects? Well, for the screws, vacancies, and this should be actually interstitials. For the screws, they're not going to interact with vacancies or interstitials. But for my edge dislocation, the vacancies are going to diffuse into here, and the interstitials are going to diffuse into there. Just like we talked about several times in class and in other problem sets. So that's problem 1 in a nutshell. So we were lucky in terms of the result of shear stress. We couldn't calculate that value here, but expect to be able to calculate on the your exam. So now on to the second problem.